Hey there, I wanted to do a video with just doing a quick channel update and answer a couple of questions. And they're questions we've covered before, so don't want to dedicate full videos to those. So what I'm going to do is do a channel update and then answer those questions. And I will put timestamps in the description below to where those start if you don't want to sit through the entire thing. Oh, and before I go on to the topic list, several people have left donations via the PayPal link recently, and it's very much appreciated. Thank you. I don't really try to monetize the channel in any meaningful way, so it's really helpful. So again, thanks a lot. Okay, so my notes. A couple topics in finance that have come up. One fellow asked about pricing barrier options, and I had no idea, so I've been reading up on them, and it seems like an interesting topic. So I do intend to do a video on that, although it's probably going to be pushed off later until later in this series of videos. The second financial related topic is the Ornstein-Uhlenbeck process. I think I pronounced that right. One of the guys is Dutch, Ornstein, and Uhlenbeck was German. So that's probably going to be a couple of videos. Basically, it's a mean reverting stochastic process. In many ways, it's similar to a Brownian motion, except with some mean reverting characteristics. So I will probably end up doing several videos on that, a sequence of videos covering what is mean reversion, how would you test for it statistically, how would you kind of construct a time sequence that follows this type of process, that type of thing. And the fellow who suggested this topic also left a recommendation for a book, which I haven't had a chance to check out, but I will get around to it and maybe incorporate some of that into the video, or a sequence of videos, better said. Then we're going to go back to just basically straight numerical methods to solve kind of physics and engineering problems. There have been several requests for videos on eigenvalue problems and how those relate to boundary value problems, which we've done via the shooting method. So there have been several questions on that, so we will do that as well. There's a bunch of videos I want to make again on boundary value problems using kind of more advanced numerical methods. A technique called orthogonal collocation to simplify is the wrong word, to speed up the calculations of these type of problems. And for the remainder of this video, I just want to answer a couple of quick questions. Someone asked about the calculation of theta and why his numbers may not agree with the platform. I couldn't tell from the question whether there was some error or is it units. We've talked about the units of theta before in option pricing, or in the video we did on the Taylor series and the Greeks, I basically did a brute force symbolic calculation in the computer. I didn't work it out by hand to calculate the derivative of the option price with respect to time, and that comes out to be a positive value, where theta is always a negative value on the platform, for long options, of course. So I just want to quick talk about why that is and where the error in those two numbers might be coming from. And lastly, someone asked if I could just do a quick video on the implied volatility calculation using Newton's method, but with VBA, Visual Basic, for applications. So I'm just going to quickly go over it. I've already written out the code. I'm not going to kind of do it in semi-real time because I feel like we're beating a dead horse with this topic. But I'll just show that quickly. And again, there'll be timestamps to both of these. If you're interested in a specific topic, I'll put timestamps in the description below. So let's actually, that was a very long introduction. Let's actually get on with it. So as I said in the intro, one of the questions I got was on put options and calculating the Greeks. In particular, he was having issues with theta. And the question was asked in the comments on this video on Taylor series. So I'm going to assume that some of the problem was here. Now, there are a couple things here. First, we had copied a slightly modified version here of code we had written in a previous video on how to calculate a Greeks. And this is basically just the formula for theta copied from Wikipedia, just wrapped in a function, and it returns some value. Now down here, we also have the Black-Scholes. I'm going to have to modify this because I wrote this for calls. I'm going to shut off the recording a bit and modify this to handle both calls and puts. But right now it takes the Black-Scholes price of an option, in this case a call, and then manually, or not manually, symbolically does the differentiation via computer so that we don't have to worry about it, and it outputs a bunch of Greeks, and then down here we make use of those. So there are a couple things I want to say about this first. So first, let me modify this function to handle puts as well as calls. Okay, so I have modified this. Where did I put it? To handle different contract types. So calls, puts, it's just an if statement and it returns the Black-Scholes formula for the calls and puts, and then again does the symbolic differentiation. So for theta, I'm going to use an example of Apple, and as of this recording, actually the day before the recording, the stock closed at with 34 days to expiration at a stock price of a little more than 134, strike price in 120. The risk-free rate I have been kind of taking as 1% in these videos, but I looked up both the T-bill, current T-bill rates, 3-month T-bill, and the Euro-dollar futures, and they both say that interest rates are effectively zero. So I'm going to use 0.0003, which is the current T-bill rate. And the implied volatility off of the platform, and I'm using Tastyworks, was this. So about 32 and change, almost 33%. And the platform said that my theta was about -4, little less than -4. So let's use let's call it theta, we'll call it Wikipedia, the function above that basically implemented the Wikipedia formula for theta. So sigma SKRT, and we're dealing with a put here, and let's just print that out. So print theta Wikipedia. Oh, it's beginning already. Minus 14.5. That's not this number. And I know we have talked about this before, but I just want to drill it in here. And there's something I want to say about this plot. Where do we do theta? Here, when we get there. So, okay. Let us look at the using SymPy to differentiate the function. So I'm going to call this, it returns a whole bunch of things, remember, if you've seen that video. So I'm going to call that, I don't know, I'll call it T. And the function was called return time Greeks, I believe. Yep. And the format is the same. So sigma SKRT and put. And let's just call it theta SymPy. I think this is an I here. And that is equal to the second element of that vector. So let's print this out. So print theta SymPy. And this takes a bit. Okay, so I found a typo in the function. I fixed it now, so we're getting this for our, we'll call it the analytical theta, or theta SymPy. It agrees out to almost all the decimal places, but the sign is different. So what's going on here? Theta for a long option is always a negative number, or zero, right? It always decays down to zero. So why are we getting a positive number? Well, let's go back up to this plot here. And notice I plotted a theta here, or the time here, going from 1 year all the way down to 0 years as we go to the right. So I flipped left and right in the axes here. So let me unflip that up in the code here. And where is it? Here it is. Run. So here we have time kind of running in the normal direction, going from 0 all the way up to 1 year. And notice that this plot here is always has a positive slope, which should make sense, right? As you go out farther and further in time, like further and further expirations or whatever, the time value of that option increases. But your platform always tells you how much it decays per day, so it effectively is the negative of this. So that's why I flipped the axes around on this, so that we don't have to kind of artificially introduce that minus sign like you would on writing code for a trading platform. So here I just flipped it back to the way I had it before, and now there's our negative slope. So when we calculated this here, it returned that positive slope, which is this positive 14 down here. So to fix that, well, that's easy. We just take the negative of this, minus, run. It returned that positive slope, which is this positive 14 down here. So to fix that, well, that's easy. We just take the negative of this, minus, run. Oh, I'm sorry, it's not this one we have to negate. It is this down here. Cool, but 14 is still not 4. So what's going on here? And I know we've talked about this before, but remember the units for theta are in years. In the Black-Scholes model, the option price, the time variable, is denoted in years. So your platform will give you theta in days, not years. So let's just divide this by 365. And since SymPy is so slow, I'm just going to copy this out since they're giving the same numbers now. So let's do theta Wikipedia, and we'll just divide it by 365. So that still doesn't look right. But remember, theta on a platform is per contract, not per unit of share, unlike delta, which is, you get a 0.16 delta option is 0.16, equivalent to 0.16 shares. But theta, for whatever reason, is per contract. So we need to multiply this times 100. And now we're basically there. We differ by, what, about 1%? So I think that's all I've really got to say about this. Check your risk-free rate. Check your the sign of your theta if you're using my SymPy stuff up here. And check to make sure your units are right, so that time is in days, and that you're looking at per contract instead of per share. So I don't think I'm going to update the GitHub repo to reflect this, since it's not really has anything to do with the Taylor series stuff we did earlier. Okay, let's transition over to the second question on how to calculate implied volatility. Okay, so just a quick review on how Newton's method works. This was a Python notebook I used to kind of demonstrate that with this cubic equation here. We're going to need the derivative of that equation. And here is the actual code that implements it, but I just want to walk through it kind of manually first. So remember, the first step in Newton's method is just to pick a guess for the root. So in this case, I picked 2. And then using the derivative, we calculate the equation of a tangent line, and you find the place where that tangent line meets, crosses through 0. And here it happens to be at x equals to 0. So here I calculated it here using 2 as our initial guess. And then you just basically iterate. So 0 is your next guess. Let's come up here and do that. Let me see, where is it here? 0. So our new guess of the root is about minus 1.333. Here's the tangent line again, so let's just update it. Let's just copy this. Come back up here. Update. So our new guess is this. You see we're getting closer and closer to the actual root. Oops, I missed the minus side on that copy. So let me do this. Paste. I think I deleted the semicolon here, so put it back in. And you see we're getting closer and closer to the actual value, which is about 0.70 something. So in Python, we implemented this with a while loop here. So we kind of save our guess of the root. There's the function value, our function derivative, and this is our update rule. So our new root guess is basically minus the function value minus the divided by the derivative plus the old guess, and you just keep iterating until some desired tolerance is reached. So now let me fire up Excel, and we'll just basically reproduce this, and I'll just talk through the Excel code because it's just the same as this, essentially, just with slightly different command syntax. Okay, so here's the spreadsheet. I think I zoomed in a little too much, but oh well. So I've already written the code here. Here's the parameters we've been typically using for this type of thing. So if you click the button, it calculates the implied volatility down here, and it took a total of 3 iterations to do so, 3 iterations of that while loop. So let's actually just look at the code and talk our way through it. Okay, so here I've predefined all the variables we're going to need, pull in the stock price, strike price, risk-free rate, and time to expiration from the spreadsheet. And this time is already in years. If we go back to the spreadsheet, I took the number of days and just divided by 365 to put it into years. So I grabbed the option type here, call or put, from the spreadsheet too. These are just predefined variables. We had the same thing in our Python code. This is my guess of the implied volatility, because remember, you need to guess the initial root. I have a maximum number of iterations of what is this, 10,000. Some tolerance checking variables, and a count to keep track just to make sure we don't run astray. So it's just a simple while loop, just like in Python. While epsilon, which is our error between our distance from the root, essentially, while that is greater than the tolerance, we just keep executing this root. And if there is if the count runs over the maximum number of iterations, just to avoid infinite loops, we break out of it. Again, here is our storing of the current guess of the root. I check to see if it's a call or put. If it's a call or put, I use the call Black-Scholes function, put Black-Scholes function. Vega is the derivative. Conveniently in Black-Scholes, you can calculate analytically what the derivative is, and that just turns out to be your Vega value. Again, here's our update rule, and then here's our checking of the error tolerance. So that's all there is to it, really. And down here I have some utility functions. I just calculate Vega. This is how we calculate Vega in the while loop. Call price, a function that returns the put price. And yeah, that's all there is to it. It's just the same code translated into a Visual Basic. We use the normal distribution function a couple times here. This is how you call it here. This false refers to a cumulative or the actual density function. Since in calculating Vega, we do not need the cumulative distribution, we set it to false, and this just acts as the density function. Down here, where do we have it here? Right here again, this time we need the cumulative distribution, so we set this variable, set this argument to true. The other thing we need is the natural log, and that's the function here, and then the rest is just arithmetic. It's just the same as the Python code, essentially. Yeah, so again, pretty simple. It's just the same thing as the Python code. Oh, I should say that Excel does not handle divide by zeros the same way NumPy does. So if you get a 0 in the denominator in this spreadsheet, it's going to crash and give an error. I didn't do any error checking because we've talked about this before, so I didn't feel like reinventing the wheel for yet another implied volatility video. Another issue, I mean, this is going to have the same issue that we had in Python. If you get a 0 Vega, you're not going to get a solution. If you have no root, in other words, if your option price, if you're talking about an in-the-money option whose price is less than the intrinsic value, it's going to crash because there's no root to that function, and that happens in Python as well. So yeah, I will put both the spreadsheet up on GitHub, and I will also copy the Visual Basic script into a text file. Again, the links will be in the description, just in case you don't want to download a macro-enabled spreadsheet to your computer. So cool. Thanks a lot for sticking around, and I will talk to you later.